Okay, acid-base calculations. We're going to use ice tables and our familiar methods solving for X, as well as our knowledge of Arrhenius and Bronsted-Lowry theory to solve problems involving pH, pOH, etc. for strong and weak acids and bases. So, the big tip here is construct an ice table and then use the series of formulas for pH and pOH, etc., as well as your skills from equilibrium calculations to be able to solve these problems. You will have to make a decision on which equation you're going to write. For strong or weak acids, you really can use either Arrhenius or Bronsted-Lowry. It doesn't matter. So just pick one. Here I chose Arrhenius just to give an example with that. For strong bases, you should definitely use Arrhenius theory, and for weak bases, definitely use Bronsted-Lowry theory. So here I'm showing the Bronsted-Lowry theory for a base. Now, you can check your Ka and Kb tables in your textbook, but you'll find the strong acids at the top of the Ka table with very, very large Ka values. So they're not even quantified for you. But just a quick refresher there, that we have perchloric and nitric, as well as hydrochloric, hydrobromic, and hydroiodic. Now, sulfuric acid, H2SO4, is also a strong acid, but it is diprotic, meaning it has two hydrogens. Okay, we are not going to be solving problems for polyprotic acids. So you're going to be solving problems in the homework, on the test, and on the exam where the acid only has one hydrogen. So not sulfuric acid or phosphoric acid or boric acid, anything like that. Okay, so that's the brief introduction there. When you construct your ice table, if you're using Arrhenius theory, water's not shown in the equation, and so you'll have an entity, or you'll have an entry for all spots on the ice table. If you're using Bronsted-Lowry theory, water being the liquid will not show up in the Ka or Kb expressions, and so you will blank the water here. Now, if you've written the equation for an acid, you'll have hydrogen or hydronium ion forming, and keep in mind then that the equilibrium concentration of that hydrogen ion is the hydrogen ion concentration used in the pH calculation. Also, if you were to find the hydroxide ion concentration of the solution, Kw over that value would be a quick answer. If you've written an equation for a base, then hydroxide ions being produced, and that at equilibrium is the concentration used to calculate the pOH. And so any of those formulas from our toolbox can be used. I've just given a couple indicators of how this concentration could be helpful. We'll go through various examples now. So copy down example 1 and choose your theory, Arrhenius or Bronsted-Lowry, and set up an ice table. Okay, so as we read the question, we realize we're being asked to find pH and pOH of a 0.015 mole per liter solution of hydrochloric acid. So the first thing I would recognize is that this is an acid, and ask yourself if it's strong or weak. So check out the Ka table or the list of strong acids. If it's not strong, it's weak, and it turns out hydrochloric acid is a strong acid. So because it's a strong acid, I have used a single arrow forward in the equation. Notice it's not an equilibrium arrow, and that's because this molecule will ionize 100% of the time. And so as you go to complete the ice table, you'll realize if we're starting off with 0.015 moles per liter of that molecule of HCl, that in fact we lose all of that. It's going to drop to 0. With this arrow, that means 100% ionization. All of the molecules are going to be ionized. And so if this dropped by 0.015, then this one increased by 0.015, and the same thing over here. And so I plus C equals E, and I'll have 0.015 for each of these. So we're asked to calculate the pH. So this value here is the concentration of the hydrogen ion at equilibrium. So in the solution at equilibrium, which really equilibrium is not even established because we had the forward reaction only. And so the hydrogen ion concentration of 0.015 moles per liter can be used to calculate the pH. So the pH being the negative log of the hydrogen ion concentration. If you used Arrhenius theory, then you have hydronium in your formula. Sorry, if you use Bronsted-Lowry theory, then you have hydronium in your formula at this point. And so the pH that I'm calculating is 1.82. Now, just like to remind you here for sig figs, this concentration here has 2 sig figs. Follow the regular rules, but for pH, it's the digits after the decimal that need to be equal to the sig figs. And so 1.82 is 2 digits after the decimal for 2 sig figs. Okay, now we found the pH, and we were also asked to find the pOH. Well, if you know the pH, quickest way I think to find the pOH would be to subtract from 14. And so we subtract and have a pOH of 12.18. So does that make sense to you that a pH of 1.82, right, would that be a pH of a solution of hydrochloric acid and a high pOH? Hopefully it does, because acids have pHs less than 7 and pOH is greater than 7. Okay, so for a strong acid, do you really have to show this ice table if it is always going to 100% ionize? And I would argue, no, you know what, you can save yourself some time here. So if you're doing a strong acid calculation and you want to quickly throw up the Arrhenius theory equation here, whatever that 0.015, whatever that concentration is to start with, you can essentially collapse your ice table, follow the mole ratio, and essentially show that you have 0.015 moles per liter of the H positive, and if you needed the chloride ion concentration, you'd have it there. However, it's really the hydrogen ion concentration that was then useful to find the pH. And so it's not necessary to construct the full ice table as long as you understand the development of it. The idea that strong acids, and bases for that matter, ionize or dissociate 100%, and so you lose all of that original amount, which means that's what's increasing for these monoprotic acids. Okay, so number 2. Now I'm asking you to calculate the hydronium ion concentration of a 0.82 mole per liter solution of sodium hydroxide. Actually, for the strong base, it will be easiest to use the Arrhenius theory, and so I'm going to rephrase this just to ask you to calculate the hydrogen ion concentration. Okay, so start with an equation for the dissociation of this strong base. And that reminds me, I don't think I've reviewed with you the strong bases. So strong bases are groups 1 and 2, oxides and hydroxides. So look at your periodic table. Sodium is certainly group 1. Sodium hydroxide is a group 1 hydroxide, and therefore that would be a strong base. Calcium oxide, magnesium hydroxide, those are strong bases. Now, iron 3 hydroxide, no, iron is not a group 1 or 2 metal, and so that hydroxide compound is not a strong base. Okay, so back to the problem. Calculate the hydrogen ion concentration of a 0.82 mole per liter solution of sodium hydroxide. So definitely, as I said at the beginning, for the strong bases, use your Arrhenius theory, and so we show the dissociation of that ionic compound into its ions. And we can set up the ice table. So we're starting with 0.82 moles per liter and none in each of 0 in each of those ion concentrations. Now again, because it is 100%, we're essentially going to lose all of this down to 0, which means this will increase by the same amount. And so again, if you wanted to collapse this ice table, that would have been fine. Okay, so what's relevant for us now? Well, this hydroxide ion concentration. Now that we know this hydroxide ion concentration in solution, this becomes like a problem you did in yesterday's work. We determine the hydrogen ion concentration by doing Kw divided by that hydroxide. And so 1.0 times 10 to the negative 14 divided by our concentration of hydroxide. And so we determine that the hydrogen ion concentration is 1.2 times 10 to the negative 14 moles per liter. We had 2 sig figs in each of these values and 2 sig figs in the final answer. Okay, example 3. Calculate the pH of a 0.10 mole per liter acetic acid solution. So we can see we're dealing with an acid, but it's a weak acid. And so the percent ionization is not 100%, so that's definitely going to affect our ice table. We've been provided that information, it's 1.3%. So Arrhenius or Bronsted-Lowry, I'll use Bronsted-Lowry in this solution because I haven't used that yet, just to model that for you. And so go ahead and complete the ice table as best you can. Okay, and so I used Bronsted-Lowry theory, made sure to blank the water because it's a liquid in the ice table. The initial concentration of this solution, 0.10 moles per liter, and as those molecules react with water, only 1.3% of them ionize. So 1.3% of that original concentration is 0.0013. So that's what's subtracting here, and because the ratio is 1 to 1 to 1 here, it's also increasing on this side. 0.1 minus the 0.0013 gives me this value here, and similarly I plus C equals E. So what have we been asked to do? Calculate the pH. Okay, so again, this concentration here of the hydronium ion is very useful for us. So we know the hydronium ion concentration. Can you now calculate the pH of this solution? Okay, and so I use the formula, substitute the hydronium ion concentration at equilibrium, and determine the pH is 2.89. Again, notice the sig figs, there's 2 in the concentration, the 1 in the 3, and so there's 2 digits in the pH reading. Now, I didn't ask you to do this, but could you have gone ahead and calculated Ka of acetic acid at this point? Well, certainly. You have these equilibrium concentrations. You can write an equation for Ka, substitute, and solve. So there's a few different ways we can go when we're asking these questions. All right, number 4, a solution of chlorous acid with that concentration has a pH of 1.36. Here you're being asked to calculate Ka. So see what you can do to figure this out. Start with your ice table. Okay, so I've constructed my ice table, noting that chlorous acid is a weak acid, and therefore I need the equilibrium arrow in my equation. I have 0.20 moles per liter of the molecules of HClO2, and I recognize that that's going to ionize, but not 100%. I'm not really sure what that decrease is at this point because the percent ionization was not provided. So what was given? Oh, the pH was given. So what could I do with the pH here in order to help me start to complete the ice table? Well, if you recall, the pH relates to the hydrogen ion concentration at equilibrium. So can't we use the formula 10 to the negative pH in order to determine that hydrogen ion concentration? That would tell us this value here. So if I want to fill these in as X right now because I don't know them, then I realize that I'll be able to determine X right here from the hydrogen ion formula. And so I realize that this is the value now for the hydrogen ion concentration, which is X, and that tells me that's also going to be the concentration of the chlorite ion, and I'll be able to calculate the equilibrium concentration of HClO2. And finally, knowing all of those, I can write my equation for Ka, substitute, and calculate. Okay, and so I rounded to 2 sig figs since I had 2 digits after the decimal in the pH, calculated the concentrations of the chlorite and HClO2 particles, and then wrote my equation for K and substituted, computing the Ka value to be 0.012. Okay, moving on, example 5, and I think we only have a couple left. So I'm asking you here to predict the percent ionization of a particular weak acid. So just to give you a little bit of help with that, this ice table here, I've said this is your initial concentration here of the HA. However much this drops by, that's what the hydrogen and anion concentrations increase by. And so we end up with this value of X here. Well, that percent, how much that dropped, really came from this value divided by the original one times 100. So what percent is X of the HA? That's basically what we're solving for. So I'll just draw your attention to this formula here, okay, which you can feel free to use. The idea is that if you knew X and the original concentration of the HA, then you'd be able to calculate the percent. And so when you look at what we've been given, we do have the initial concentration, we just don't have the value of X. Well, if you don't know X and you're looking to find it, if you can write an equation for K, in this particular case Ka, substitute your expressions and solve for X, then you'll be able to know X and complete this calculation. So why don't you start by setting up an ice table for nitrous acid at 0.25 moles per liter to begin with. Complete your ice table, look up the Ka value in your textbook appendix, and set up your equation, substitute, and solve for X. And if you're really understanding what's going on, then you can finish up calculating the percent ionization. Okay, so I have set up the ice table here using Arrhenius theory, looked up the Ka value, found from the question 0.25 moles per liter, and realized that that was ionizing to some small percent, which I subtracted here. 0 and 0 plus X gives me my equilibrium concentration expressions. And now I need to solve for X. So after substituting, I see that on the left side here, or on the right side, sorry, I have X squared over 0.25 minus X, and we can see that that right side is definitely not a perfect square. The denominator is the problem. So I won't be able to use the perfect square strategy. So I'll have to check the approximation. So that initial concentration of 0.25 divided by the Ka value is just over 100. It's 543. And so that approximation is greater than 100. And so we'll be able to shrink that binomial down to just 0.25. And so that's going to give me a much smaller solution at this point. So I'll need to take the square root then of 0.25 times the 4.6 times 10 to the negative 4 and determine X. Okay, and so the value for X rounded to 2 sig figs, 0.011. So that means that's the hydrogen ion concentration, right? It's also the change value for these monoprotic acids. And so the percent ionization is essentially that value of X, the 0.011, over the original concentration of molecules times 100. And so we finish up with 4.3% ionization. And yes, normally the weak acids are somewhere between 1 to 5%. Okay, last example, number 6. Acid or base, what do you think? N2H4. Acid or base? Hopefully you're thinking base, Bronsted-Lowry base, and remembering the lone pairs on that nitrogen can accept a proton. It's certainly not a group 1 or 2 hydroxide or oxide, and so it's not a strong base, it's a weak base. For weak bases, you definitely need to use Bronsted-Lowry theory. So begin this ice table by writing a balanced equation for the weak base of hydrazine, N2H4. So you can complete the right side and then complete the ice table as much as you can. Okay, so the approximation works. We can solve for X, 5.0 times 10 to the negative 4. And so we see back up here that X is the concentration of the hydroxide ion at equilibrium. And so we've been asked to now find the pH of this solution. And so if we know the concentration of the hydroxide, how do we find the pH? You really have a couple of choices as to the steps that you can do from here on in. So this is something that you've done in an earlier lesson. So go ahead and pause the video, find the pH of a solution with a hydroxide ion concentration that we now have, and then check back with the video. Okay, and so I found the POH, looking for 2 sig fig, so I went with 2 digits after the decimal in the POH, subtracted from 14 to find the pH. And does that make sense that the pH of a weak base would be close to 11? And it most certainly does. We know that pHs greater than 7 are for basic solutions. All right, so you'll see that we followed the same really pattern every time. We set up the ice table, complete what we can, solve for X if necessary. Otherwise, there's other information given that allows us to figure it out, and then calculate what we're looking for. There's certainly all those pH and POH formulas that we manipulate as we go.